Hello and welcome to everyone. My name is Supriya Gupta Bani, Assistant Professor of Computer Science and Engineering with Data Science from Ramdev Baba College of Engineering and Management. Now today's my topic is medical image segmentation area and its technique. So let's begin with the brief synopsis of the lecture that is given with this topic, medical image segmentation. Now, what is medical image segmentation? So, medical image segmentation is a computer vision task that involves dividing an medical image into multiple segments, where each segment represents a different object or structure of intersects in the image. The goal of image segmentation is to provide a precise and accurate representation of the object of interest within the image, typically for the purpose of diagnosis, treatment, and planning with the quantitative and qualitative analysis. Medical image segmentation is an innovative process that enables surgeons to have a virtual X-ray vision. It is highly valuable tool in healthcare, providing non-invasive diagnostic and in-depth analysis. With this in mind, in this post we will explore the UI medicine and GI tract image segmentation with the Kaggle dataset. As part of this analysis, we will utilize PyTorch and with PyTorch Lightning. Medical image segmentation is a process that involves dividing medical images such as CT scan or MRI scans into distinct regions or structure of interest. This technique is used to identify and isolate specific areas within the image, which is crucial for diagnosis, treatment, planning, and monitoring of diseases. It can be done manually by experts or automated using computer algorithms and machine learning processes. Medical image segmentation plays a vital role in various medical specialties and enables quantitative analysis and precise measurements. So, we are going to discuss with you the coordinate system in medical imaging. Three types of coordinate system commonly used in imaging applications: the word anatomical and the medical image coordinate system. We will talk about anatomical coordinate system. This system has three plane and data set we will be using in on axial plane. Medical data set containing lung CT scan of patient diagnosed with pulmonary fibrosis, a disorders with no known causes and no known cure, created by scarring of the lungs. Prognosis of the troubling diseases become threatening for the patients because outcome can range from long-term stability to rapid deterioration, but doctors aren't easily able to tell where an individual may fall on that spectrum. This is where data science can help in predicting the deteriorating condition of the patient. What are the problems faced in medical image segmentation? Medical image segmentation faces several challenges including image variability. Disparate image characteristics make creating a universal segmentation algorithm challenging. Ambiguity and complexity. Complex structure, ambiguous boundaries, and overlapping regions complicated accurate segmentation. It means the ambiguity and complexity is a major challenge to handle the image segmentation, where we cannot define exactly where is the boundaries, where is the complex structure can defined with the segment. The next limitation is limited labels data. The scarcity of annotated medical image hampers developing and evaluating segmentation algorithm, where we have not labeled data as a training or test data, where we cannot identify which type of image can be labeled. Is it a cardio related image? Is it the brain related image? Is it the liver or spine related image? That could not labeled, so we cannot use these unannotated medical images for the segmentation. We have to use the pre-processing techniques and image processing techniques to refine this data. So this is the major challenge to define the segmentation in medical imaging. Next complexity is the computational complexity. Large data set and high dimensional images required substantial computational resources and time. What is the high dimensional data? It means the data has various coordinates to store and to verify, that could contain the resources as well as the computational time. So this is the complexity of finding the image segmentation. Next one is validation and generalization. Now, ensuring accuracy and applicability across different modalities, populations and clinical settings is difficult yet and crucial. Now, building the image segmentation of the medical image data set, as the task is to segment organ cells in the image. The competition provides that the data set is in the form of 16-bit grayscale, and this is in the PNG format image, and the ground truth segmentation annotations are RLE encoded mask provided in a CSV file system. Some observation about the dataset is it contains 115488 samples with multiple rows for each patient's of cases. Out of these rows, only 33913, it means 29.364% have RLE annotations for the class. This number denotes the total number of annotations available. The total number of image with corresponding annotations is 16590. These images belong to 85 cases patients, where each patient has multiple scan for each day on multiple days. Now, load and convert the image from unit 16 to unit 8, where the format using load image method. Get the data frame groups rows in train.csv file for the image and decode the RLE encoded mask for each class using RLE decode method for each image. Then the RGB mask is converted to a grayscale mask single channel, where we can use 0 to 255 grayscale values to convert it this RGB mask, and where each pixel values has indicates the class ID of the pixel. The process is done using the RGB to 1 hot to gray function. It means this RGB is converted with 1 hot encoding to the grayscale values, and save image mask pair in their respective folder. It means we have to store this pair of RGB values and this grayscale values images as well as in the same folder. Now, what is DICOM? In previous lecture we have discussed with DICOM file format. Again I am going to use this DICOM for image segmentation. A DICOM image file is an outcome of the Digital Imaging and Communication in Medicine standard and represented as .dcm extension. Because of its ease of integration and continuous evolution, this communication standard has over the years achieved a nearly universal level of acceptance among vendors and radiological equipment. So, this DICOM is a file format where we can see that all the data, date, diagnosis reports, images are collectively stored of a patient in the file format that has the extension of DCM. DICOM differs from other image format because it groups the information into dataset. DICOM file contains of the header and the image data collectively in one file. We will see later how these groups of information looks like and interpreted. Now, conversion to Hounsfield unit. The Hounsfield unit scale is a quantitative scale for describing radiodensity in the medical imaging CT scan and provides an accurate density for the type of tissue. Plain X-ray, which only display 5 densities like air, fat, soft tissue, bone and metal. This CT displays a huge range of density ranging from air could be considered as black and to bone and major density values like called bone with the white. Now on Hounsfield scale, water represented by 0 value and air is represented by the value of minus 1000 HU. Black on the gray scale and the below white and the bone between plus 700 values to plus 3000 values very dense bone, we can consider it as a white in your gray scale. So, as bone are much denser than surrounding soft tissue, they show up with very clearly in CT images with this HU units. Now, the raw pixel values of images get converted into Hounsfield unit because the spectral composition of the X-rays depends on the measurement setting like acquisition parameter and tube voltage. By normalizing the value of the water and air, water has the HU 0 and air has the HU minus 1000. The image of different measurement are becoming comparable. Now we are analyzing the CT imaging where physics of CT scan we have discussed about this. Computed tomography CT uses X-ray beams to obtain 3D pixel intensity of the human body. A heated cathode release high energy beam that is electrons which in turns release their energy as X-ray radiations. Now, X-ray pass through human body tissue and hits a detector on the other side. A dense tissue that is bone will absorb more radiation than soft tissue that is fat. When X-ray are not absorbed from the body that is air region inside the lung and reach the detector, we see them as a black. Similar to a black film, on the opposite dense tissue are depicted as white. In this way, CT imaging is able to distinguish density differences and create a 3D image of a full body material. Here we can see the CT scan image where we can see the air portion is going to use the black portion that its HU unit is 0. The bone portion which have the density is very high, so it will containing the white line portion and that has plus 3000 or plus 1000 above HU range. The fat portion is going to plus 700 range of HU unit and it's showing you the grayscale images in the point of pixels with gray. Now, the step is finding the pixel dimension to calculate the area of this dense function, the air function and the fat function. So, clearly stated that we have to define this image into the preprocessed form with HU units, and whenever we define this HU unit, we can find the different portion of area like air, like dense bone, like fat bone, and fat portions are there, and define this different type of density area with the different type of HU points. Now step 2 is binarize image using intensity thresholding. The expert learns to be the Hounsfield unit ranges of -1000 to 300. To this end, we need to clip the image range to -1000 to 300 HU unit and binarize the value to 0 to 1. So, we will get something like this portion. Here we can see whenever we convert our image into grayscale image 0 to 255, now we have to convert it with HU form. When we convert this in HU form, you can see -1000 to 300 HU form is created here, and simply we can see the dense portions are going to given with a white pixels, and the air portion and low intense portions are given with the black pixel, that is containing with -1000 to -3000 HU, and the white portions are containing 0 to +3000 HU units. Now step 3, contour finding. For computer vision, a contour is a set of points that describe a line or a area. For each detected contour, we will not get a full binary mask, but rather a set with a bunch of x and y values. We care about the lung region that are shown on white if we could find an algorithm to identify closed sets or any kind of contours in the image that may help. After some search, then we find the marching squares method that find constant value of contour and image from SK images called SK image dot measure dot find contour. After using this function, we visualize the detected contour in the original computer tomographic images. Here in this image, we can see clearly that the contour image can define with the different type of rectangle and triangle areas. Suppose if the black portion is containing a lower HU and the grayscale containing the higher HU values, after this contouring, the red line will making the contour of each section. Like if we consider the left black portion, all the portion is contoured with the red line. Similarly, with the right portion, right basin, we can consider all the red line areas is considered as a red portions of lining. Now, we are moving further with step 4. Find the lung area from a set of possible contours. The contour of lungs must be a closest set, that is always true. The contour must have a minimum volume of 2000 pixel to represent the lung. That may or may not include the body contour, resulting in more than 3 contour. When that happens, the body is easily described by having the largest volume of contour that satisfied the pre-described assumptions. Now with this code, we can see that we have loaded image. Now we are finding the contour of the image. Now how we can find the contour of the image? We have to process first the HU analysis of the image. after analyzing the HU volume, we have to define whenever the HU volume is greater than 2000 values, it defined as contour line. It means the major portion that is defining with HU are going to use to make the contour forms. So, the volume contour is decided with your HU volume, and after that each and all portion has divided with lungs area with the body image, and the lung contour is decided with your HV form. As an edge case, I am showing that the algorithm is not restricted to only two regions of the lung. Inspect the blue contour below. Here we can see whenever we contouring the image with the high value of HU, you can see here the forms of contour with the red line portion, and the second one is formed with the contour of the green line portions, and the blue portion is again making a different type of contour where we can see the lung portion not containing only 2 or 3 portion, it can be contain more than 2 portions with this contouring. In next 5, contour to binary mask. Next we save it as a nifty file, so we need to convert the set of points to a lung binary mask. For this I have used the Python library that is draws a polygon, where draws a polygon and creates a binary image mask. Then I merge all the masks of already found lung contour. Now here in the code we can see when we are going to perform the lung mask, we have to load the image from the NP array. Now we are going to finding the contour for x coordinate, for y coordinate, and polygon tuple we have to make with this x and y coordinate. Finally, we have to mask this image of np.array image and going to perform this lung mask with the mask function. After masking, we have to return this lung mask image, and we are going to process the masking on this. The desired lung area in 2 mm square is simply the number of non-zero element multiplied by the 2 pixel dimension of the corresponding image. The lung area are saved in as CSV file along with the image name. Finally, to save the mask as nifty, I use the value of 255 for the lung area instead of 1 to be able to display in Nifty viewer. Moreover, I save the image with the fine transformation of the initial CD slice to be able to display meaningful alignment without any rotation conflicts. Finally, I opened the mask with a commonly nifty viewer for Linux to validate that everything went okay. Here are the snapshots for 4 slices. Here we can see that in the image finally we got the HEO unit, and after contouring and masking we have find the 2 major portion of the lung areas, whichever given in the white portion with higher HU units, and after masking we can see in the blue format that yes, 2 exact lung areas are visible after the masking. Now segmentation in the main vessel and compute the vessels over the lung area ratio. If there is a pixel with an intensity value over -500 HU inside the lung area, then we will consider it as a vessel, because the image segmentation is going to find out what is the dissimilarity between the original image and the upcoming images. So we have to find this vessel's area. So first we do element wise multiplication between the CT image and the lung mass to get only the lungs. Afterward, we set the zeros that resulted from the element wise multiplication to minus 1000 air in HU, and finally keep only the interstices that are bigger than minus 500 as vessels. Here in code we can see we have to define the vessels formed with minus 1000 mass, and then vessel is greater than equals to minus 500 HU, that will be considered as 1, and if the vessel size is less than 500 it will considered as 0. Then we show the sliced vessels and denoise the image with the denoising image segmentation. Now finally we show the sliced vessel as an output. Here we can see the sliced image with your vessel imports in your lungs. Here we can see the black and white portion, the vessel intensities are given in the following curve. You have the two lung portion, and this lung portion is giving some white dots as your vessel contains. As you can see, we have some part of the contour of lungs when I believe we should like to avoid. To this end, I created a denoising function that considered the distance of the mask to all the contour points. If it is below zero point 0.1, I set the pixel value to 0 and as a result exclude them from the detected vessels. Below you can see the differences between the diagnosis image in the right and the initial mask. See, in this image we can see clearly stated that masked image can be denoise the extra vessels points whichever we see in the last picture. Now we clearly stated that the segmented image has two portions of lungs and the white dots are displaying us the vessels containing the white dot portions with a clearly intense value of pixels. There are no noise in the masked image. If we overlay the mask of the original CT image, we can get that this image can show us the higher HU intensity value with the two portion of black image that contains your two portion of lungs, and the blue image of masking can show the lower level of gray image, can be air, can be lower side of fat. So this can be your image can consider as hard portion as bone and lower portion as normal HU unit. After masking, we have to find the noisy portions are removed, the clear picture is with us, and the segmented units are clearly visible with the contour image. Now you have a solid understanding of CT image and their particularities. We can do a lot of awesome things with such rich information of 3D image. So I am going to conclude this topic of image segmentation, where we have used majorly the lung image or lung CT image for segmenting. So we have done all the portion of the CT scan imaging understanding, that is solid understanding of CT images, that particularized with various steps of pre-processing techniques and segmentation technique. So we can do a lot of awesome things of going to perform or information on the 3D images. So the different type of steps we have followed to segment the images. First, acquiring the image, that is CT image you have to taken for lung portion. Then we have to file the OpenCV image and convert this image into ICODMA form, where the file has storage all the images and all the information of patients in that file unit. Then we have to convert it in CSV form. That CSV file has containing all the information of that image portion. Now we have to pre-process this image as going to use your HU units performance, where we have to done the HU units where lower portion has containing as air and hollow portions, and the major density portions are going to show you the bone portion. that containing from -1000 to +3000 HU units. After converting this, we have to denoise our image, where the major portion of denoising object we have to remove from our major image. Now we have to done the masking of the image. Now masking is done, the images has converted into inverted binary conversion, and with the contouring you have to decide the portion, or the contour line can decide the portion is segmented by your original image. Like we have done here with the lung images, we contour the image with the points, and we have decided that there is two portion are contoured with a single array points. So the contoured image can show two portions are in front. We have decided that yes, 2 points or two contour portions are in the lung portion, and after that we have finding the vessel portions from this segmentation images. We have masked, we have applied denoising, we have applied HU units, we have applied the contouring portion and finding all the segmented portion of the lungs area. Now we can use the final output from this data set. You can consider all type of data set and images from GitHub and Kaggle, and the medical imaging can be converted with this pre-processing techniques and segmentation technique. What is segmentation is going to do for you, that the portion you require that can be extracted as object for your reference, or the portion can be detected from the previous one or for the background. So the image segmentation is very important area in the medical image processing, where we can segment our required object from the given pattern or given image. After that we have to decide what the diagnosis, what the treatment should provide that patients. So storing their all the data with the file format, then pre-process their data with the pre-processing technique, and then finally segmented area find out can be help for the further processing of analysis and diagnosis of the images. So the segmentation, image segmentation of medical image plays a very important role in the image processing techniques. So the medical image segmentation is performing that your interested area or your interested object or your interested structure can be differentiated with the image you have provided. So the image download and to process the images, and after that we have applied this image segmentation to provide a precise and accurate representation of the object that is your interested area, or that is the interested area of the researcher as well as the medical practitioners. If the medical practitioners required the lung areas and have to diagnose this lung area, you have to segment this lung area from the input image, as well as if your medical practitioners or researchers have to diagnose the brain skull area, you have to diagnose the cardiac area. So you have to segment this cardiac and brain areas from your medical image processing. So the medical image segmentation plays a very important role to define your interested area to segment or extract your structure from the given medical images.